So question number 4, it has a 25 points, and the questions are again here. The transfer function G1s is the same like this one, and over here we have first to see the value of K2 such that this loop should have two equal poles, negative real poles, and then we have to find out the range of K for which the system is stable. In the second part, we have to find out the value of K1 so that the system should have the oscillatory response, and to find out the frequency of oscillation. Then we have to determine the condition number 5, like if the complete closed loop should have a pole 8 minus 5, so what will happen to the system? We have to test the system behavior, like can it be approximated by the second order underdamped system. And the last part is very simple and straightforward, to find out the overshoot and the settling time of the system. So let us proceed to solve the problem. So first we take this closed loop. In this case, if I write this transfer function in the simple format, it will become 1 over s cube plus 6 s square plus 8, and this closed loop is suppose G inner loop GIS. Then I can write very easily that GIS is equal to here it is S will be equal to 1 over S into S square plus 6S plus 8 whole divided by 1 plus K2 S divided by S into S square plus 6S plus 8. The simplification of this will give us 1 over S into S square plus 6S plus 8 plus K. So this is the transfer function of the inner loop. Now the question is to find out the value of K2 such that this K2 is the same, such that the system transfer function should have two equal poles. So in this case, if we choosing K2 is equal to 1, GIS can be written as 1 over S into S square plus 6S plus 9. Now it is easy to see that GIS has two poles at minus 3. It can be found from this one, like S square plus 6S plus 9 is equal to S plus 3 whole square, and definitely if I make this equal to 0, so S will be equal to minus 3 comma minus 3. So this system will have two negative poles 8 minus 3, and they are real, so the condition is fulfilled. Now we have to find out the value of K for which the system is stable. So in the next slide we will find this condition. Thank you very much. Now we can resketch the block diagram like this. Over here we have the plant, the inner loop, which is equal to 1 upon S into S square plus 6S plus 9, and the feedback loop is K1, and here we have plus minus. The closed loop transfer function T of S can be easily written like this: K1 upon S cube plus 6S square plus 9S plus K1. So to find out the stability criteria, we will draw the Ruth Hurwitz's table. So here it is easy to make the table. Like for S cube, we can write 1. The coefficient over here is 1, so here it will be 1, and then we can write maybe 9, and after that of course it is 0. If you don't write even, then it's okay. In the next one it will be 6 and K1. This will be S square. So then writing the element at this place, it is easy for us to find out. This will be minus 196 K1 upon 6. After doing this all calculation, we will get 54 minus K1 upon 6. So here we can write 54 minus K1 upon 6, and here definitely we will be getting 0. So this is for the S, and S to the power 0 straight away here it will come K1. So we need this should be greater than 0, and this one should be greater than 0. So here it gives us 54 minus K1 upon 6 greater than 0, implies that K1 should be less than 54, and here we need for the stability, because all of the first row elements should be positive, so I need this should be positive, and we need also this one should be positive. So this will remain positive whenever K1 is less than 54, and here K1 is greater than 0. So it gives us the condition that if K1 is less than 54 and greater than 0, the system will remain stable. So this is the stability condition. Now the question is to find out the value of K1 such that the system should oscillate. So to fulfill this condition, we need originally, like this row, both elements should be 0. So we consider 54 minus K1 upon 6 should be equal to 0. This implies K1 is equal to 54. So for K1 is equal to 54, the system will oscillate, and in this case we have to find out the frequency of oscillation. To do this, the closed loop transfer function we know can be given by Ts is equal to K1 upon S cube plus 6 S square plus 9S plus 54. So the frequency of oscillation to find out, if I put over here it is 6, and here we will have 54. So if we cancel them, it is 1 and this is 9. This means PS is equal to S square plus 9, this and equal to 0. This means the frequency of oscillation S will be equal to plus or minus J3. This means the frequency of oscillation omega n will be equal to 3 radian per second. So this will give us the frequency of oscillation. Now the question is in the C part to find out the value of K so that one of the pole is this -5. To proceed for this, first we consider the closed loop transfer function as we determined in the previous sheet. T of S is equal to K1 upon S cube plus plus 6S square plus 9S plus K1. To one of the pole will be at -5. If we can write this K1 upon S plus 5 into S square plus AS plus B. The remaining task is to find out the value of K1 such that these two equations are satisfied. So here if we consider this denominator polynomial is equal to A of S, this will be equal to S cube plus 6S square plus 9S plus K1, and the multiplication of these two can be easily written like S cube plus 5 plus A into S square plus 5A 5A S plus B into S plus 5B. Now comparing the coefficients on both sides, we get 5 plus A is equal to 6, like this 6 is equal to 5 plus A. So this will give us A is equal to 1. Similarly, we take 5A plus B is equal to 9. So 5A plus B is equal to 9 will give us B is equal to 4, and K1 is equal to 5B. So we will get K1 is equal to 20. This means if we choose the gain of the controller 20, then the closed loop will have one pole 8 minus 5. Now the closed loop transfer function we can write like T of S is equal to 20 upon S plus 5 into S square plus S plus 4. So here we can consider like from this one omega n square is equal to 4. This means omega n is equal to 2, and zeta 2 zeta omega n is equal to 1. This will give us zeta is equal to 1 over 4. This means the damping factor is equal to 0.25. This means damping factor is less than 1 and greater than 0. So the system is an under damped system. Over here the real part of the pole like zeta omega n is equal to 0.5, and the pole of the first order system P1 is equal to minus 5. This means the first order part this means the transient of the first order. This means the transients. This means the transient of the first order part will finish 10 times faster than the underdamped part. So we can approximate the transfer function T of S by this transfer function 4 upon S square plus S plus 4. Now the next part is asking the question. Now we can find out the overshoot and the settling time. If I rewrite the transfer function of the closed loop, T of S, which is equal to 4 upon S square plus S plus 4. So it is easy to see that omega n square is equal to 4 implies omega n is equal to 2 radian per second, and 2 zeta omega n is equal to 1 implies damping factor is equal to 0.25. Now to find out the percent overshoot, we know that percent overshoot is equal to exponential minus damping factor pi upon square root of 1 minus damping factor multiplied by 100. This will be giving us e to the power minus 0.25 into pi upon square root of 1 minus 0.25 square. This will be approximately multiplied by 144.42, and the settling time T of S we know is equal to approximately 4 upon zeta omega n. So this is equal to 4 divided by 0.5, which will be equal to 8 seconds. So thank you very much for watching this solution.